In this video, we're going to take a look at our first nonlinear graphical model. So we've been talking all through this video series so far about lines and how great of a tool lines are for modeling the relationship between experimental data. But we've always been hinting at the idea that lines won't always work to model some kinds of data. So finally today we've come to the point where we have to deal with a nonlinear kind of graphical model. Our first nonlinear model is called a square-dependent model. And as we go through this video, hopefully you'll come to see why we call it that. So what do we do if a line isn't a good model? Well, sometimes a line isn't a good model because the data is just random and there just really isn't any relationship that would be a good model for the data. This would be an example here. This scatter plot shows a sort of a really weak linear correlation, but basically these points are all over the place and probably you will not be successful making any kind of a model. But there are other cases where there's some pattern there for sure, but it just doesn't happen to be a line. So this would be an example. Thinking back to the video about experimental design, when we talked about the diameter of wires and their strength, this is some data that would be collected from an experiment like that. When we make a scatter plot of this data, this is what we get, with diameter as the independent variable and strength as the dependent variable. We find that there's a kind of a curve to this data. And if we do regression analysis, it's not really super good. The R-squared value is 0.9778, which isn't horrible, but it's not really great. And the R value, not much better. But the thing that's even more telling is, if we look at the shape of the scatter plot, if I kind of trace through these points, I see this sort of an upward curving shape. It's not just random scattering around the line. There seems to be some other pattern that's going on there. So we want to look for some kind of a pattern that correlates to that. Take a look at this data. We have some X and Y values here. So these are just random numbers, not data. Can you see a pattern? Inspect the numbers that are the X's and the numbers that are the Y's and see if you can tell how they're related to each other. You may have noticed that all of the Y values are the square of the X values. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. When we graph this data, we get that same kind of a shape, that upward curving shape that we saw with the strength and wire diameter data. This is a parabola. You may recognize this shape from math class. That generally upward curving relationship between X and Y is what we call a parabola. And parabolas have this Y equals K times X squared relationship. So mathematicians, if you look at this, that's how they think about it, but scientists also can think about it this way. We could think that if we have Y on the vertical axis and X squared on the horizontal axis, well, this would just be the equation of a line where K is the slope. And if you plot the X squared values on the horizontal axis, in fact, they will all be exactly the same as the Y values, and you just have a line with a slope of 1. Here's another one. Do you see the pattern? Here we have every Y value being twice the square of the X value. 0 squared is 0, times 2 is 0. 1 squared is 1, times 2 is 2. 2 squared is 4, times 2 is 8, and so on. When we plot this data, we get that same kind of a shape. So we get this shape no matter if we just are squaring the X values or if we're squaring them and then doing something else with it, like adding a number to it or multiplying it by a number. We still get that same shape. And once again, if we squared the horizontal axis values, squared the X's, we would find a straight line pattern. So would that work for this data? Well, I've done the calculations here. In the pink highlighted row on this table, we have all the squares of the diameters that are in the top row. If we plot that, here's what we get. Looks like a straight line. Doing regression analysis, and in fact, it's a perfectly straight line. So what this is telling us is there is a line where y is equal to some constant number, which is the slope of this line, times x squared in math terms. But for us, that means the strength is equal to the slope of this line times the diameter of the wires squared. So that's a relationship between the diameter of the wires and the strength. You can predict how strong a wire is going to be by just squaring its diameter and multiplying by the slope of this line. That's a square-dependent relationship. And using the value that we get for the slope from the regression analysis, now we actually have a predictive tool. Square any diameter of a wire, multiply by 226.6 newtons for every square millimeter, and you will get the strength of that wire in newtons. So let's summarize. If you have a scatter plot that looks like this, the relationship is going to be the dependent variable is equal to a constant number times the square of the independent variable. And how you find out the value of that constant number? Well, you replot with I squared, the independent variable squared on the horizontal axis, and keep the dependent variable on the vertical axis, find the slope of that line, and that's the k that goes in that equation. So this is our first look at a nonlinear model. A line doesn't really work, but we can find a way to manipulate the data so that we can get a line that does work and just happens to not have the independent variable by itself on the horizontal axis. We just changed it a little bit. It still gives us a very good predictive model. So that tool, linearizing a square-dependent relationship, is something that we will use from time to time as we investigate data in science.